This lesson introduces aromatic heterocycles, which contain heteroatoms. I'd like to begin this topic by examining two very common nitrogen-containing heterocycles, pyridine and pyrrole. Using frost circles of these two compounds, along with the fact that they both contain 6 pi electrons, we can see that pyridine and pyrrole are both aromatic. Their stabilized bonding orbitals are all completely filled. The orbital pictures next to each structure are meant to demonstrate to you the number of pi electrons donated to the aromatic pi orbitals by each atom. Electrons colored red are part of the pi systems, while those colored black, including electrons involved in the sigma bonds, are not part of the pi system. The most important difference between all-carbon aromatic compounds and heterocycles is the presence of lone electron pairs on heteroatoms. A critical question we need to be able to answer is, does a given lone pair contribute to a cyclic pi system or not? In pyridine, we see that the lone pair resides in an sp2 hybrid orbital, part of the sigma set of molecular orbitals. The nitrogen atom contributes only 1 electron to the pi system because that's all it needs to contribute to satisfy the octet rule. In pyrrole, on the other hand, nitrogen's lone pair resides in a 2pz atomic orbital, where it overlaps with other 2pz atomic orbitals to form the molecular orbitals of the pi system. In an upcoming webcast, we'll use this idea to rationalize the relative basicity of pyridine and pyrrole. Now, let's turn our attention to resonance structures of pyridine and pyrrole that contain charges. Our goal is to understand why pyridine and other heterocycles containing 2 connected or N2 nitrogens are considered electron deficient, while pyrrole and other heterocycles containing 3 connected or N3 nitrogens are considered electron rich. Let's begin with pyridine. You should notice that the C-N double bond in pyridine is a good electron sink. That is, we can reasonably push electrons toward the nitrogen atom, leaving a negative charge on the nitrogen atom and a positive charge on one of the ring carbons. Furthermore, we could move the positive charge around to all ortho and para positions relative to the nitrogen atom, as shown here. These resonance structures illustrate that there is a significant amount of partial positive charge spread out over carbons in the ring. Thus, these carbon atoms are lacking electrons and are considered electron deficient. Remember that recognizing the C-N double bond as an electron sink, or electron withdrawing group, was the critical observation here. In pyrrole, the situation is quite different. Now there are no pi bonds to push toward nitrogen. However, we can recognize the N3 nitrogen atom as an electron source, or electron donating group. Pushing electrons from the nitrogen atom, we can see that negative charge is distributed on carbon atoms in the 5-membered ring. Because of the excess negative charge on carbon atoms in the ring, we call this ring electron rich. In the next lesson, we'll investigate some of the important differences in reactivity between electron deficient and electron rich rings.